In order to convert the kinetic energy of waterfalls and tides into usable electricity, humans construct dams and enormous turbines. Chinese researchers have just invented a lightweight power generator that is based on carbon nanotube fibers. This generator is suited for converting even the energy of flowing blood in blood arteries into electricity, which will allow for the production of hydropower on a much smaller scale. They write about their breakthrough in the scientific publication known as Anjuan Chemi. People have been harnessing the power of moving or falling water for thousands of years to accomplish their goals. At first, this energy was used to drive mechanical devices like water mills. Later, it was used to generate electricity by taking advantage of height differences in the landscape or tides in the ocean. The use of naturally flowing water as a sustainable power source has the advantage of having, virtually, no dependencies on the weather or the amount of daylight that is available. Even bendable, microscopic power generators that operate by utilizing the flow of biological fluids are not out of the realm of possibility. A study group from Fudan University in Shanghai, which is located in China, has provided an explanation of how such a system may operate. A fiber with a thickness of less than 1 mm has been produced by Weisheng Peng and his colleagues. This fiber generates electrical power when it is surrounded by a flowing saline solution, which might be in a thin tube or even in a blood vessel. The fundamental idea behind the fabrication of the fiber is not complicated at all. A polymeric core was encased in an ordered array of carbon nanotubes that were wrapped continuously around the core. It is common knowledge that carbon nanotubes are electroactive and mechanically stable. Additionally, one may spin them into sheets and arrange them in rows. When the electroactive threads were finished being manufactured, the carbon nanotube sheets had a thickness of less than half a micron when they were coated over the fiber core. For the purpose of producing electricity, the thread, which the scientists refer to as a fiber-shaped fluidic nanogenerator, FFNG, was either submerged in moving water or repeatedly dipped into a saline solution. Both of these methods produced the same result. The scientists indicated that the production of electricity was the result of the relative movement that occurred between the FFNG and the solution. A symmetrical charge distribution is disrupted as a result of the flowing solution, which results in an electrical gradient running along the fiber's long axis. This is how the theory describes what happens when an electrical double layer is formed around the fiber. This system had a very high efficiency in terms of the power that it produced. It was reported that the FFNG showed a greater power conversion efficiency of more than 20% in comparison to other types of small energy harvesting devices. This was the case. Other benefits include flexibility, tunability, lightweightness, and one-dimensionality, all of which contribute to the intriguing technological applications that may one day be possible. Simply winding the sheets of FFNG around a substrate made of elastic fiber will make it possible to stretch the material. Wearable electronics become an extremely intriguing possibility for the FFNG application when they are weaved into fabrics. The extraction of usable electrical energy from the circulatory system for use in medicinal applications is yet another fascinating application of this technology. The preliminary examinations using frog nerves came out positively.